So how do you calculate the reaction quotient? This is the procedure for calculating the reaction quotient. Well, it's a quotient, so it's a fraction, right? There's a numerator and a denominator. The numerator is calculated by multiplying the activities of the products of the reaction, what you wrote as the products when you wrote the chemical equation. But you have to raise your each activity to a power equal to its coefficient in the chemical equation. You do the same thing for the denominator, except in the denominator you do it for the reactants. So, in other words, reaction quotient is some quantity based on the activities of the products divided by a quantity based on the activities of the reactants. Let's illustrate that with this example right here. What would be the reaction quotient for this reaction? What are our products? H2 and magnesium ions. So what is the activity of H2 gas? The numerical value of the pressure in the partial pressure of H2 in atmosphere. So it's partial pressure of hydrogen. Okay, it's unitless. Okay. Now keep in mind when I say partial pressure of H2 here, I'm only referring to the numerical value. If you really want to be strict about units, you can say that's pH2 over P naught, and P naught we say, like in this case, would be 1 atmosphere. So if like you have 0.5 atmosphere over 1 atmosphere, then the ratio of the two is just 0.5. Okay, but things can get cumbersome if you do it that way. If for precise, if you want to use precise mathematical language, that's what you have to do. That's what we do in physical chemistry, okay? So anyway, it's P over P partial pressure of H2. What would be the activity of magnesium ions? These are ions in solution. So what would be the activity of that? Molar concentration. So I'm going to write Mg with a +2. So that's my numerator. To what exponent should I raise my H2? What's the coefficient of H2 here? It's 1, so raise to the power 1. If you raise something to the power 1, you don't have to write the 1, right? And to what power should I raise my magnesium? Also to the power 1, so I don't have to worry about putting that. So divided by, what about a solid? What's the activity of a solid? Go back to the previous slide. Activity of a solid is 1. Pure solid or liquid, activity is 1. So 1. And what's activity of H plus? It's an aqueous solution. It's a solid, so concentration of H plus. But what should I do with that? Raise that to the power 2. Okay? So that's how you calculate your reaction quotient. You figure out what's the partial pressure of H2, what's the concentration of magnesium in moles per liter, what's the concentration of H plus in moles per liter. Plug it into this expression. Make sure you don't forget to raise the activities to exponents corresponding to the coefficient in the balance equation. All right, so let's look at this example right here. How would you calculate Q for this? Given that at a particular instant you find that H2S is 0.1, H3O plus is 0.15, and sulfide is 0.020. What would be our Q for this one? It's going to be H3O plus raised to what power? Products over reactants, right? Raised to the power 2. Concentration of, what's the other product? Sulfide, raised to what power? 1. So I don't have to write 1, right? Over H2S. It's an aqueous solution, so concentration of H2S raised to what power? 1. And do I do concentration of water? No, it's just, what's the activity of liquid water? It's actually the solvent here, mole fraction, but for practical purposes, that's just going to be a 1. And raised to what power? 2. So 1 squared is still 1, right? So you can just ignore that one. All right, so let's plug in our numbers. What are the numbers? H3O plus is how much? 0.15 squared. And sulfide is 0.020 divided by H2S, which is 0.10. Okay? So our reaction quotient in this particular case is 0.0045 or 4.5 times 10 to the negative 3. And it's a unitless quantity. Okay?